We want to solve matrix equations using inverse matrices. We haven't spoken about matrix equations thus far, but they're remarkably what they sound like, an equation of matrices. And the reason behind this is solving matrix equations combines all of the skills we've learned to really test our mastery of the individual concepts, but it also forms the foundation of every linear algebra topic that underlies matrix applications. Fortunately, due to being virtual this year, we won't be going into applications extensively. However, being able to solve matrix equations will allow us to do many applications that we wouldn't be able to do otherwise. And this is really where we start getting into things like cryptography, computer security, animation for digital models and video games. So it's a really rich field. And really these 5 lessons are at best an introduction into linear algebra and matrices. So I hope it's something that you'll feel inspired to continue studying later on in college. To get us started, I want to really start looking at just refreshing ourselves with some strategies for solving matrices. And when I say solving, I also mean if we are inverting a matrix or reducing it to reduced row echelon form, RREF, these are things to look for. So first, you want to look for columns that have the same or same but opposite numbers, like 5 and -5 or 6 and 6. These will quickly allow us to cancel one of these numbers, either by adding or subtracting our 2 rows. Next, we want to look for columns with 1 or -1, such as 2, 1 and -1, 5. In this case, we're able to get rid of one of our numbers. And by get rid of, I mean reduce it to 0, simply by adding or subtracting a multiple of 1 row. It's worth pointing out also that although I'm writing these as column vectors, as long as they are part of a larger matrix, we're able to use these strategies. Columns with multiples of each other is another place to look for. So if we have 5 and -10, we can use this 5 to get rid of our -10 by adding 2 times the first row. 12 and 6, we could get rid of our first row by subtracting 2 times the second row. So looking for those common multiples is really helpful. Lastly, if none of those things are available, look for columns with, quote, easy least common multiples. For example, we could find the least common multiple for 2 and -3 and 17 and 25, but I can say immediately that the least common multiple of 2 and -3 is going to be 6, whereas I need to use a calculator to find the least common multiple of 17 and 25. So looking for those opportunities where we can simplify more directly will help us develop that intuition to efficiently and confidently solve our matrices. So solving matrix equations with inverses. This is where we are really going to build up the concepts that underlie what a matrix equation is and how we solve it. So consider the following system of equations: x minus 2y, that should probably be a, that should be, let's see if I can change this. I don't know if I can. I cannot. Okay, so point being, there is a mistake here and I shall fix it. So this should really be a plus 3z. Equations shouldn't have multiple equal signs. So x minus 2y plus 3 times z equals 9. Negative x plus 3y equals -4. 2x minus 5y plus 5z is equal to 17. We can rewrite this as an augmented matrix, pairing the coefficients 1, -2, +3, -1, 3, 0, 2, -5, +5, and then what our equations are equal to, 9, -4, and 17. Typically, we would write this as a solid line. The formatting options wouldn't really allow me to do that, hence why it's just the dots. We can also write this as a matrix equation. So we take our matrix, we call this A, hence down here A, and then we have a column matrix of our variables, x, y, and z. Now remember, when we multiply matrices, let me change color real quick. This is a 3 by 3 matrix. This is a 3 by 1 matrix, 3 rows, 1 columns. So the interior numbers match, and the product is going to be a 3 by 1 matrix carrying the outside numbers. So this is all defined by matrix multiplication. When we multiply, we're multiplying pairwise our first, our second, and our third components. Ideally, I probably should have done these in different colors, just to differentiate it better. When we multiply these out, we would in fact end up with the equation that we started with. So by multiplying through our matrix operations, we're reconstructing the original system of equations. And then of course it's equal to this column vector that is the constant from each equation. To just put this into words very explicitly, A is the coefficient matrix of the system of equations. X is the variable matrix. Notice that this is a capital X, not a lowercase x, and it has components x, y, and z. And B, over on the right side of the equal sign, is the solution matrix. So this is what our equations equal. So how would we solve this? We can't just reduce the matrix to reduced row echelon form, because we now have to consider how the multiplication works. But then, as it turns out, we can't divide by a matrix, but we can multiply by an inverse. So if we multiply both sides on the left by the inverse of A, as shown here, notice that on the left-hand side, A inverse times A is equal to the identity. Anything times the identity is equal to itself. On the right-hand side, we have multiplication on the left. The reason why we have to specifically multiply on the left is, number one, in this case, multiplying on the right wouldn't be defined. And number two, because matrix multiplication is not commutative, meaning we can't change the order and guarantee the same product, if we do the same thing on the left and the right side, we have to multiply on the left side on both sides of our equation. So we can solve a system of equations using a matrix equation and matrix inverses. Again, this brings together everything we've done into one idea. So we're going to start off with one example, and then we'll do a couple more examples in following videos. So we want to solve this system as a matrix equation. The first step is to actually write it as a matrix equation. So we're going to start with our coefficient matrix. So this is going to be 3, -2, 1, -1. Again, that's just taking the coefficients. So this would be our matrix A. Then our variable matrix is going to be our variables. In this case, our variables are x and y. So this is what we would call our bold capital X. And it's equal to the matrix of what our equation is equal to, so -1 and 0. And this would be B. So this is just setting up the equation. Next, we need to find the inverse of A. So find inverse of A. So to do this, we're going to augment our matrix, 3, -2, 1, -1 with the identity matrix 1, 0, 0, 1. And this is where we get into using our row operations to get our left-hand matrix into reduced row echelon form. So our goal is RREF, reduced row echelon form. Notice that I have a 1 here, so I'm going to make row 2 my pivot, and I'm going to have row 1 minus 3 times row 2. So that'll be minus 3 plus 3 in our second component, because we have this -1, minus 3 times -1 is +3, minus 0, and then minus 3 as well. So our new first row is going to be 0, +1, 1, -3. Now I will fill in our second row, which hasn't changed in this first step. But notice that the second component of our first row is now a 1, so we can very easily cancel out the -1 in the following row. So if we have row 1 plus row 2, that will immediately cancel this out. So plus 0, plus 1, plus 1, and we're adding, so it would stay a -3. Writing down below, we have 1, 0, 1, -2. 1 minus 3 is -2. Carrying down our first row, which has not changed in this step, we're just copying down. Now, remember, in order to be in reduced row echelon form, we have to have that descending staircase of 1s. So our very last step is going to be to swap rows 1 and row 2. So we would have 1, 0, 1, -2, and then 0, 1, 1, -3. And so our first portion has become the identity matrix, which means the second portion is our inverse matrix. So if we come up here for a moment, let's copy our equation so that we can carry it on down. Oops, that might be too far. Okay, so now what I'm going to do is move this over some so I can illustrate in one go how we're going to be using this inverse matrix. And might as well continue in the blue. So we multiply both sides on the left by A inverse. So that's 1, -2, 1, -3. And again, on the left, so that's 1, -2, 1, -3. And over here on the right-hand side, A inverse times A is just the identity matrix. So essentially, these two matrices cancel out. And what we're left with is X is equal to the product of A inverse, there should be a little minus sign there, A inverse times B. So to do our multiplication, we have A inverse, 1, -2, 1, -3. And then -1, 0. The nice thing about matrix equations is that this multiplication is always a square matrix, generally speaking, times a well, it would need to be a square matrix or it doesn't have an inverse, times a column matrix. So it's really 1 times -1, which is -1, and then plus -2 times 0. So that's just -1. And then 1 times -1 plus -3 times 0. And so this is also equal to -1. And so our solution, xy, is equal to the matrix -1, -1, which we can also say x is equal to -1, y is equal to -1, or we could write it as -1, comma, -1. This would be our solution. And to check our solution, we just go back and plug it in. So if we come up to the original equation, 3 times -1 minus 2 times -1, well, that's -3 plus 2 equals -1. And then -1 minus -1, -1 plus 1 would give us 0. So it does check out. We can do this anytime to make sure that our work is correct. And here we have found that it is in fact correct. As I said, in the next video, we will do a couple more examples, possibly one example per video, and then that will be it for our unit on matrices.